Hello everybody and welcome to Handmade Hero, the show where we code a complete game live on stream. We are doing some lighting today. Just catch people up to where we are because obviously lighting is a pretty complex topic, so we've got a bunch of things that we need to be working on and that we need to get right. So just a real quick overview of where we're at and what we need to do this weekend. If we take a look at where, let me just do a quick recompile just so you can see the fresh build. So there's our compile, here's the run. You can kind of see where we left off. This is debug mode, by the way, so we're still in the kind of slow version of it. Although our debug build's not that slow right now because since we're not running the lighting transport. So we did a lighting test, and the way that we did it is we put a purple light at the top and a yellow light on the bottom, not running light transport. So we're just hard stuffing those values as if that light was ubiquitous everywhere. And then we tested our reflector function to make sure that it actually worked, and it does appear to. So as you move around, you can see you hitting basically the mirror surface there, and that all appeared to work right. So we believe our pixel sampler is, our pixel shader is sampling from the volumes the way, because we also tested a number of other aspects of the volumes. We believe it's sampling properly. What that means is we can now start moving towards the full sampling of it. And in order to do that, what I'd like to do this weekend is get us to the point where still not doing any lighting transport, because again, we have that code, so it won't take us too long to like sort of rehabilitate that and start to work with it to get the actual lighting transport working. Because if you remember, we already had that working in a different version of the lighting pipeline. But in this new lighting pipeline, we have it turned off because we're just working on the pixel shading. So what I'd like to do this weekend is start stuffing simulated lighting values that actually sort of relate to things we might actually find, right? So when I'm hopping around in here, what I'd like to do is, let's say we take the location of the player, for example, and we stuff lighting values into our light probes. You can see all the light probes are being drawn there, right there, those little hovering cubes. Suppose we stuff lighting values into those cubes, right, that represent something like a local light source emanating from the player. And then what I'd like to do is verify that we can get our pixel shader working well to sort of sample the lighting that results from that. And the idea behind this is, before we switch over to working on the light transport, I want to verify that if we stuff predictable lighting values into our system that sort of relate to the kinds of lighting values we hope to get out of our light transport, assuming it's good, do we get acceptable results in the actual game? Because if we don't, we need to keep working on that pixel shader, because obviously, no matter how good our light transport is, if the pixel shader that samples the result of the light transport sucks, then the lighting sucks. So we have to make sure that we get that part correct, right? And so what I'd like to do first is, yes, stuff those values, and then verify that we get reasonable results out. Then, after we've got that totally settled, which maybe, if we're really lucky, will be done by the end of the weekend. So we can just check that off, and then we move on. So if we're lucky, we get that done by the end of the weekend, and then we just move on to the final phase of lighting, which is working on getting the light transport to run fast enough through the system so that it can be still at 60 frames a second, and so on, right? And there's lots of things we can do to try and make that happen, including like subsampling, like which light probes get updated each frame, and we can restrict the light probes that we're sampling to only the ones in the view, and all sorts of things that we can play around with there, as well as just straight up optimizing that path. There's a bunch of stuff we can probably do to fix that part as well. So looking at the system as a whole, that's going to be sort of the final phase of lighting. And so what we're trying to do this weekend is set ourselves up for going into that part of the process, right? And so let's get started on that. It's pretty clear what we want to do. So let's kind of move forwards on that. All right, so the first thing I want to do is just play around with that pixel shader a little bit because before we try to stuff more interesting lighting values in there, I want to still play with directional lighting as we have in there right now, where we're stuffing in like a yellow light and a purple light into it specifically. I want to go ahead and take a look at that lighting, which is right in here. You can see the lighting equation that we're computing right here. And if you look at what this lighting equation is doing, it's pretty straightforward, right? And I can break it out a little bit more just to kind of give you a better idea of what's actually happening, right? And there's a couple different things that we want to be able to do here, but yeah, and you know what? I think I want to say there's also a bug in this lighting equation that we didn't really look at, and I could be wrong about that, but we'll just take it as we go. So a couple things here, and I'll explain the bug that I think is in here as I break it out. If we take a look at what the components of our lighting equation are right now, which, like I said, was just a basic one we threw in there, a very simple reflection, which is not what we really want. So that's why I want to kind of beef it up a little bit and get it a little more interesting before we move on to stuffing other values in. We've got a couple different terms here. So the first thing we have is a term that's telling us what the incident light versus the outgoing direction to the eye is, right? And that's sort of a specular bounce term. So that's like a reflection coefficient, right? And you can see that reflection coefficient, it's right here. And so this coefficient here, ref C, it's taking the inner product of the light normal and the sample normal, right? So that's the direction that goes to the light and the direction that goes to the sample. And so if we're sample meaning like the so the direction that goes to the light, which is the incoming, the direction that the light's coming into this surface, and then the sample direction is like the eye direction, right? It's where we're looking at it from, or whoever wants to sample this. It doesn't have to be the camera. We happen to be calling it the camera right now, but you could sample the lighting in any direction you wanted. So those two, as they become coincident, so if they're pointing in exactly the same direction, then we get the maximum contribution from this light source, right? And as they separate, we get less. Does that make sense? And so that's what we kind of want to see there. Now, it's worth noting that this part of the equation, again, like I said, we haven't really worked this through yet. So I think we also have some kind of buggy parts here, or at least nomenclature problems as well. And so we kind of want to now take the time, since we just did this at the end of the last stream, we want to now take the time to start to work this through, get all the bugs out of it, make sure we're sampling it properly, and at least try to verify it as well as we can. So if you take a look at what happens in the main part of the shader, you can see us sampling all of our actual lighting incoming lighting values, and then we specify what the actual parameters are from what the actual directions of those incoming lights are, which we happen to know because they're just the cardinal directions, right? That's how we're storing our lighting in our light probes. And so when we look at what happens, what we pass in is the direction to the light and then the reflection vector, right? And so really, when you look at this, this is not an accurate name for this thing. It's not the sample direction, really. What it is it's the outgoing direction, right? It's the bounce. And so what we really want to do is call this the reflection normal, because that's really what it is. And so I named it like basically what the eye direction would be, but that's not what we're passing. And so the first bug would have been a bug. If it had actually been what we'd named it, that would have been wrong. The inner product between the light direction and the reflection direction, that's correct, meaning this inner product is the thing we want to compute. But the inner product of the light outgoing direction and the eye direction, that's not what we wanted to know, right? That would not have been correct. So again, not really a bug in terms of what the code did, definitely a bug in terms of how he named it, so we want to get rid of that. Okay, now we do clamp this inner product, and that's important, right? So this clamp is very important. The reason the clamp is very important is because if we get something that actually comes out more than 90 degrees away, we don't want any reflection there, right? And so what we kind of need to make sure can't ever happen And I think we currently have the problem of this happening, honestly, is that we don't ever want this to produce a situation where you can get light transmitted sort of through a surface, because this is not supposed to simulate any... This lighting equation is not about subsurface scattering, right? This is a basic reflectance function, and we want to make sure that we're actually doing that computation. If we wanted subsurface scattering or transmission through surfaces, that's all fine, and we can try to implement something like that, but we don't want to accidentally implement something like that, because if we accidentally implement it, it's not going to be correct, right? It's going to be some kind of weird lighting function that doesn't really properly do transmission in the way it should. I'll ask one more time, does anyone know if Milton's been fixed? Someone please message me and tell me if Milton's been fixed, because I'd really like to fix our Milton at some point here. Anyway. So the part that I want to say we have as a bug right now, or at least it's, it's a bad lighting function at the moment because it doesn't have something that we want. If we take a look at what this is doing, and I'll draw the diagram again from last week, we have a surface. So this is our surface here. And this is the surface normal. We know that we're looking at this thing from some direction, so our eye is over here. This is the camera, so maybe I'll call it the camera because that's probably a better name for it. It's what we call it. We don't call it the eye. So our camera's over here. We're filming from this direction. We're looking at this particular surface. This is our reflection vector, right? So this is our reflection. I think we called this ref n in the shader just then, right? And in fact, if you look here, yeah, we don't actually pass in the surface normal into this routine yet. We will be doing that, but we don't do it yet. So we only have the ref n, and then we have the light normal. And we don't know where that light normal is right now. We just know, like, hey, the light normal is coming from some direction, right? So we've got a normal that's going out to the light source here, and we want to make sure that's pointing outward from, it's the direction the light to the light source, not the direction that the light is incoming. And so if we take a look at that, we just want to make sure that that says it. Light west is -1. That's pointing in the west direction. So that seems consistent. So I think this is correct, right? All right. So the bug that I was talking about is if you take a look at what's happening here, we've got our light normal and our reflected normal. And what we're doing here is we're saying, well, as long as these things are within 90 degrees of each other, right, we're going to get some light. Now, why is that the case? Well, it's the case because the only thing that's attenuating the incoming light in that direction is the inner product between the reflection vector and the light vector. These are these two vectors right here, right? One of them came from the camera bounce, that's our ref n, and one of them is just the incident light, wherever the light is coming from, right? And that could be anything that we want it to be for sampling this equation. But it happens to be the 6 cardinal directions because our light probes are storing their little cubes, our light probes are, and they're storing the incoming light that is found by looking in each of these directions, right? So we have no idea how this surface is oriented. It could be oriented any way in space. We have an incoming light direction. That incoming light direction is going to be based on one of these cardinal directions. We don't know how the surface is oriented. We have a camera. We don't know where the camera is. And we know that it's going to produce this reflection vector that bounces off the surface, goes in that direction. We're taking a dot product between these two. What do we know about the dot product? Well, we know what the dot product is if we took that reflection vector here and we drew a perpendicular plane, right? And then we take whatever we're sampling, like light n, right? What we know is as long as this angle is 90 degrees or less, so as long as it doesn't go behind this plane, we will get some contribution. As it goes behind this plane, the dot product becomes negative, right? And it will become -1, in fact, here. So it's negative something here, right? And it's -1 over here. Becomes negative as it passes through, ends up at -1, comes back around to positive as it passes through that plane again. What that means is that the clamp will prevent us from viewing any light from back here. So if the light direction is this way and the reflection vector is that way, we won't see anything, right? But if the light vector was this way and the reflection vector that way, we will see it. Why is this important? Well, if this is the surface, like we drew before, and this is a very plausible situation we could have constructed if the camera's here, then that means that anything, remember, anything that's on this side of this plane will give us light, including this entire region. But this region is behind the surface, right? We can't even see the surface from here. So if our reflection vector is pointing this way and our light vector was pointing that way, we would see the light coming from behind the surface, which is wrong. So unless I'm mistaken, and I mean, again, you know, I do these streams with no preparation, so I'm just working through the math on the stream exactly as you see me doing it. But unless I'm wrong about that, constructing it with the diagram thus makes it look like to me that there is an additional bug here. And the bug here is that we aren't accounting for the fact that we have a surface normal, and the surface normal has to be pointing in the same direction in order to get this light contribution, right? In other words, if we have a light that's coming from behind the surface, we shouldn't see anything. Now, arguably, we never see surfaces that are facing away from us. We backface cull those away. And so we don't really need to do any work to prevent us from having the situation where the reflection normal itself is behind the normal. Why? Because you can't actually construct that. I can't view the surface from behind the surface normal, so I won't have a reflection vector that's behind it. Because the reflection vector and the camera vector are on the same side of the surface normal by definition, by construction they will always be that way. So don't need to worry about that. But the light, not true. The light could come from anywhere. And so what I want to do is I want to take another coefficient here, and this is like our sidedness coefficient. And what I want to do is I want to say like there's a light direction coefficient, and what that is going to be is that's going to be a clamp 0 to 1 of the inner product of the light direction and the surface direction, right? And so what that means is I need another normal in here when I pass that, when I ask for this get irradiance, I need to know what the surface normal itself is. And we know what that is, right? Because we had to use it for our reflectance function. It's just this right here. So I'm going to go ahead and say this is what the surface normal is, like that. But honestly, because we don't sample multiple surfaces, what I can do here is say, look, we know it's a global, we know it doesn't change, it's just for whatever the surface we're on, so we can just put it in like that and call it a day, right? And that keeps our function simpler, its function signature simpler. If we were going to sample multiple surfaces inside this shader, which might happen if you were doing some kind of weird shader, we're not going to probably need it. But if you were doing something weird, you might want to make that parametric because you might want to sample different kinds. For us, we're always sampling the same thing, so why overcomplicate things? It's always going to be that world normal. Okay, so this is a directional coefficient that basically says, all right, when the light bounces off this surface, I expect this to tell me whether or not there's a self-shadowing going on there, whether or not basically the light is coming from behind the surface and shouldn't be transmitted. Now we're going to need this for other purposes as well, because this is only a specular equation right now, and we haven't accounted for diffuse lighting. Diffuse lighting, of course, is lighting that hits a surface and goes in all directions. We're just right now only assuming specular, lighting that hits a surface and bounces off in one direction, right? And so we need to kind of like improve that part of it anyway. So we're going to need that term, but we probably don't want to do the light DC here. We probably don't want this, right? And the reason for that is this is not just a 1 or a 0. This is actually a smoothly varying function that goes from 0 to 1. And what I want to do is I only care if it is positive at all. If it is, then I probably don't want another cosine term attenuating my inbound light, because we don't have any real reason to do that. We know that there's, I think, well, you know, I could be wrong about this, but I'm fairly certain that we don't want another cosine attenuation that's based on the incidence of the light. We only want one cosine attenuation, and that's based on the difference between the two angles, I think. Now, let me just draw that out for you, and it may be that we're wrong about this. This is a physically based lighting question, which honestly is not something I study that often. And so I could be wrong, but let me give you just the basic breakdown. So again, what happens, and we've talked about this on other lighting things before, is if you have the surface normal here, and you're talking about a light situation like this, where you've got some direction to the light source, there's the light, some reflected vector here, and you want to talk about how much light is going to bounce basically back at the viewer. So we're talking about this bounce right here. So what we try to simulate is the fact that on the surface itself, you have to imagine a patch of light, and you've got sort of inbound light rays coming at the surface and bouncing off of it, right? If they're hitting the surface directly this way, then whatever the size of the thing is, like, so what we're simulating essentially like a infinitesimal like patch, right? Because we're doing this point by point, we're simulating it. At an infinitesimal patch, we're basically saying there's some shaft of light that's coming down, hitting the surface, and the size that's hitting the surface is some infinitesimal size, right? This shaft, if we were to rotate it, right, we're still talking about how many light rays fit into that same size patch that goes in here. But what we're looking for now is this, right? This is the amount of light that can hit that patch from the side, right? And when we get all the way to here, that is really tiny. So as it starts to fall to the side, the width, even no matter what the size is, so even though this is like this is infinitesimal, very small. Even though this patch is just like effectively like an integral size patch, right? So we're just talking about a generic sized patch that we would integrate over the entire surface to calculate the lighting or whatever. So there's no real size to this thing, but it still has a dimension, right? What we know is that no matter what the size of the surface we were asking about, whether it's infinitesimally small for integration or whether it was actually a real patch of surface that was, a meter wide or something, what we know is as the light comes from a steeper angle, the amount of light that could hit it, the sort of the bandwidth, the pipe size, right, the cross section of the tube of light coming down onto it, just gets smaller and smaller and smaller until eventually there's nothing as you get to like the perfectly glancing angle, right? And so that's where our cosine theta term comes in, right? And what I don't understand, because I've never really gotten the explanation, like that part I understand fairly well. What I've never really quite gotten the full answer on, I don't understand the explanation very well, is how you know whether you need to do that for the outboundness, right? So if that comes in here, that's how much light this surface has to give off. But then you have an equivalent question, which is like, well, if I'm viewing the surface from the side, then that limits the amount of light I could let out in that direction too, doesn't it? Right? And so what I'm not entirely clear on is why we seem to mostly talk about a single cosine incident there, and whether or not it really should be a cosine squared sort of a situation. I mean, it's not a cosine squared because it's two different angles, but it just seems to me that it's a little bit weird. I don't quite get why we have that sort of differing dichotomy. Like, I don't really quite grasp the explanation. This physical explanation makes some intuitive sense to me, lightly, meaning I get where they're coming from when they say, well, as you imagine it coming from the side, there's less room for the light to hit in, so assuming a uniform field of light coming in, as you get down to an incident, a glancing angle, you're going to get less and less of that light collected. I just am not clear about the irradiant part of that. So when we then go to radiated outwards, shouldn't the same thing be true? Meaning I can only send out a smaller part of light if I'm looking at the side, right? And maybe, let me just check. Let's see if we can find one. Because that's basically what you want to know with lighting, right? Like, you want to know these terms, how they do the fall off. But the point is, we need to know whether we want to account for that extra cosine in there or not. We would do two different equations depending on the circumstance. So if I go over to it, something physically based running like, let's see, specular lighting equation. Let me see if we've got anything that seems reasonable. I don't have any idea which of these things would be actually useful. Yeah, I really just don't know. But we can try to see what they end up with in their equation, right? Okay, so this is our exact diagram, which helps, right? You can see the light incident here. You can see the, I guess what is the V point in view, right? That's the light reflection unit vector, though. Which, okay, so this is not quite exactly our equation. They're phrasing it opposite. They're doing a light bounce like that, where we did the view bounce. And the reason for that is because, well, I guess there's no real penalty for us doing that. If we were to do a view bounce, So, I'm just thinking about it. It seems really less efficient, right? Because we've got 6 incoming light sources that we're trying to simulate here and only 1 viewer. So I think we did it the more efficient way for us. So we can ignore that, though. Like, it's the same equation either way. You can bounce the light or you can bounce the viewer. It wouldn't change, really, right? So I think we're okay there, but I don't think that's a good decision for us. But we can still use what they suggest. So this right here is the n.L. So that lighting is telling us how much light can hit the surface, right? And that was the part I was saying about before. Like, that tells us how much is there. So we do actually want that amount, right? And then we have the reflectivity out. They are doing an R.V as well. So it looks to me. No, they use a sum though, right? So it looks to me like they just use the diffuse by itself and the specular by itself, and they don't. So there is only one cosine fall off there, right? I mean that appears to be what happened. Again, that's Phong lighting, which isn't necessarily physically based, though. So let me take a look here. And unfortunately, we're probably not going to get a great explanation there, but we can see. I'm just looking for a diagram that would say, would just discuss that part, because I don't feel like, yeah. So I don't know. We'll have to take it offline. But that's my only question is, like, I can convince myself. A lot of these times when I read these things, I just have to kind of convince myself that I believe it, because light is a pretty tricky thing, and I don't, you can't really see it at the kinds of scales that we're talking about here. So it's like, I'm like, yeah, all right, I believe this explanation of, like, if we imagined a particular size, any size, and you want to talk about how much can hit the surface, I get that. But then I don't understand, like, why you wouldn't care on the, like, outbound side, and I don't know. There's a lot of stuff that just doesn't make good sense to me sometimes, and it's hard for me to really, like, wrap my head around, like, why it's true in one case but not true in the other case. And so I would feel better if we double checked our lighting stuff with it physically, but I don't do much lighting work, and so I would feel better if we had some verification there. But we can do that later, because again, we just need this to be roughly correct, and we can finish the rest of our lighting system, and then we can come back to this part and try to make it more in line with what we want as we go. But anyway, so if we have a reflection, the direction we want to sample, we want to see what light's coming from that direction. We've got this light DC. That's going to be important for our diffuse term, like I said before. But we also kind of need it to make sure that we don't allow mixing in of this light in the case where this is 0. So what we would like to do is effectively have a thing where we say if light DC equals 0, then ref C equals 0, right? And this is just a quick, like, sort of conditional move kind of a thing. We're basically saying, look, if we can't see the light from here because the surface itself would have blocked it, then what we want to do is make sure that we knock out 100% of the light. Now, really, we can make this be a more specific, like, we don't have to be that cagey, because what we know is that if we can't see the light from here, we shouldn't even have bothered really computing this in the first place. And so what we might want to do instead is say, well, actually, why don't we just say if the light DC is greater than 0, do the equation, otherwise don't do any of it, right? So what we may want to do is say, like, look, the result starts out at 0. We will compute this thing in the case where we actually know we can see it, but otherwise we just won't compute it at all, right? And so that, I think, is probably what we want, because in the case where we're talking about lights that can't be seen, probably most of the pixels in the warp will not be able to see it, and we'll be able to fast track that part of the computation, right? And so what you can see now as well is I think we're kind of now getting a more correct, I think, lighting. I think the reason we were seeing so much light before that I think we probably shouldn't have seen is because we weren't sort of knocking those surfaces out. However, I do think we still got, I don't think that's quite right, because when I'm looking at it here, I expect to see some yellow bounce there, and I'm not seeing it. So this may be incorrect here. If the world normal and the light, well, no, you know what? I guess that's not incorrect. Now that I think about it, that's correct. Because this surface that I was looking at there, this surface is directly perpendicular to the light source. The light source is coming from straight bottom, right? And so you can't see it if you've got a surface that's that flat to it. That's actually true. So the problem that I think we would have there is it's not immediately clear to me that that's the right answer. The only reason is because we're kind of simulating these light probes as cubes, right? And so I don't know that we want to take out all of the light that's coming from below us because it's a probe, right? And so I feel like we kind of want more of that light in there. And just to talk about just to draw out what I'm talking about there, just a little more clearly. So if you imagine what we're doing here, I think what we saw there was actually correct in that we had a wall. This is the normal to the wall. We're talking about a light that's incoming from this direction, right? So the outbound lighting direction we're looking, or the direction to the light source is completely perpendicular to the wall. So based on cosine fall off, we should not be able to see it, right? It simply shouldn't be possible to see that light source at all, because none of that light can bounce off a perfectly vertical surface. The problem is this is a light probe. It represents all of the light coming from an entire cube, right? So like this. It's going to represent all of the light coming from a cube by putting it down in here. And so we kind of end up in a circumstance where that's not very useful, because it could easily have seen light from that direction. All through here would have hit that bottom part of the cube, right? And so when we look in a direction and we want to know what's off in this direction, doing that seems bad. And while we want to prevent it from looking over here, we don't really want to prevent it from looking anywhere in here, right? And that is exactly what we would be doing by taking the dot product of this normal with this normal. You know what I'm saying to you? So I think it's a little harder than we would like. And I think what we want to do here is talk about spreads a little bit. So meaning what we'd rather do is say, all right, the amount of light you could see from here is actually, it's sort of trying to ask about a wider field of view. And it's specifically the direction to the light source. We're sort of talking about a 45-degree angle, right? That you can see out of that, like it's a 90-degree frustum, right? 45 in either direction. So we kind of want there to be an actual ability to see this half, right, of that lighting source by going this way. And we might want to account for the fact that it falls off to half, right? And there is such a thing as falling off to 0 if you manage to get all the way back here on it. But we kind of need an equation that represents that fall off a little bit better, right? It needs to be able to account for a wedge of light coming in and sort of taking that into account, right? And I'm not really sure the best way to do that, but I do think we want to do it at least a little bit. So when we're doing this here, where we're doing the light and the world normal, and we do a clamp 0 to 1, I think what we want to do here is we want to potentially bias this by some amount, some amount of bias upward, so that we can count light that's coming from a wider cone. I feel like again we're going to want to work the equations out more carefully, but I think we want something more like that, where we're allowing light to come from a wider... Oops, I didn't mean to hit the escape key. Let's try that again. I like that our logo was lit. So I feel like we do want something more like this. And so do you see how that's now getting that contribution in there? Which I think is more what we want. So I think this is a better approximation. It may be that that's a little too much, right? And so it's hard to say, but that would be the full 45. Because if you look, right, and we ask the question, well, what is... the cosine of 45 degrees, it's 0.70 blah, 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 right? And so if we wanted to talk about exactly 45 degree spread, we should probably be adding like 0.7-ish, right? And if we wanted maybe a little bit less than a 45 degree spread, we could drop that down, right? But so this value should probably be more like that, honestly. Although actually it's the other way around, so it's probably this. It's the inverse, right, of that. It's the amount you would get if you were 45 degrees off. Trying to see how let me draw this out, because I was about to say something very hand wavy there, and I want to make sure that it's not totally bogus. So we're talking about a situation, right, where we've got here is our surface normal, and we're talking about a light perhaps that is directly directly parallel to the surface. So it looks like that. And what we're saying is that, well, what we would really like to do is say that this surface looked more like this. So actually we want 0 to be when you get all the way to when the dot product, right, gets all the way to this 90 degrees plus this 45 degrees, right? So it's the 90 degrees plus 45 degrees of the dot product. That's what we actually want to see there, right? Now, we know that when we do this, just bear with me as I draw the diagram. We know that when we do this, the inner product will go to 0 here, right? Because the inner product gives us the cosine of the angle between the vectors. So if we take 90 degrees plus 45 degrees, it's not this. It's this, right? And so if we look at what that cosine is going to be, we would say, what's the cosine of 45 plus 90 degrees, right? And so when we take the cosine of 45 plus 90 degrees, we're expecting that value here, this one here, to be -7, right? So that's when it should go to 0 if we were to make it the full 45 degrees, right? It should go to, sorry, -0.7, right? So when it goes to -0.7, if we really wanted that to be the end of the fall off, so the end of the fall off goes there, right? And so we swing completely around here. Then yeah, when we do our cosine theta, we would expect us to get 0.7, and we would bump the entire thing up by the 0.7. So my 0.3 thing was wrong. We would bump the entire thing up by the 0.7, and that would give us, as if we were getting the entire range, right? That's one thing. However, what we want to be doing here is treating this as if we are still talking about cosine fall off, I think, right? So what we really want to do is map this range more consistently, right? So when we take these two vectors, we would really, if we could, we'd want to compress this down a little bit more. So rather than talking about simply jacking it up, what we may want to do is talk about shifting it and scaling it. So scaling it back down, because remember, that would make our cosine go now between the 0 clamp, which is, it can go all the way to now -0.3. We're clamping that out, right? So it's going to go from 0 to 1.7. So we may also want to multiply by 1 over 1.7, right? To rescale back those values. So I would guess it would be something like 1 over 1.7 times the inner product plus 0.7, right? Something like that. Again, not really sure this is a valid way of doing this, but it at least gives us something that approximates an inbound light for these kind of weird samples we're doing. And I'm going to call that good enough for now. We can always kind of work on our lighting equations later once we feel like we've got the rest of the system under control, right? But so now we're sampling from those light sources, I think a little bit more sanely, and off we go. Okay, so now let's work on the diffuse lighting component of this, because we only have that one reflection. Not only that, but this is not really a specular lighting equation, because normally you'd raise the specular light to a power as well. So we haven't done that yet, but we also haven't included any diffuse lighting. So to include some diffuse lighting in here as well, what we need to do is actually use our light DC to figure out how much light should probably be emanating from this surface in the first place. And in order to do that, what we would like to do is use this incident dot product to determine how much light just goes in an arbitrary direction, right? So incoming light, and then we bounce it out at basically the rate commensurate with that inner product of the surface normal and the incoming light. So in order to do that, what we want to do is, in addition to this equation, right, we would like to have a sort of a light DC term here that's going to multiply this as well, right? The light V RGB, we want that part as well, and that's the diffuse component. What we can do probably is just add these two things together, right? That's how much light would be coming in from the direct specular, and then how much light would be coming in from the light DC, right? I'm going to break it into two parts only because we probably want a specular power. We probably want to play the specular separately. So what I'm going to do is I'm going to get in here basically a light, like an inbound light. So this is a inbound like or an irradiance value, right? That's just coming in from the light source, or maybe I'll call this pure light, just the light term by itself, or unpacked light. Basically, we're sort of reconstructing what the incoming light color is. That, something like that. And so then what I want to do is I want to have that in both sides, right? So I want the light color times the diffuse amount, and then I want the light color plus the reflected amount, right? And so we're counting both of these. Now, it may not make a lot of sense to count both of these because, again, we want there's a certain amount, this surface, whatever the surface is, transmits a certain amount of diffuse light and a certain amount of specular light, or might have an actual lighting equation that it uses, like a BRDF or something, to determine how much diffuse light, how much specular light comes out at any particular point, and so on, because, lighting is lighting and it's complicated. So what we want to do is probably mix these using some sort of a surface characteristic. Some surfaces will be very specular, some will be very diffuse, things like that. And we would like some way of talking about that particular piece of information. What did I do wrong here? That is what I did wrong here. All right, off we go. And so this is now what we would expect more to see with, again, the diffuse and the reflected lighting. And what you can see is there's a lot less angular dependence. So as I get really incident where the light sampling is right off the bounce, I see more of that specular coming in. But as I come down, I don't get as much specular, right? And so that's what we would expect to see, and that's all fine. If I now change to just one light, so let's go back to our lighting, where we output sort of fake lighting information. If I go into the fake lighting information and I just stuff it with something else, so instead of what we were stuffing it with, which is like 2 directional lights, one from the top, one from the bottom, you can see that happening here. If I took out one of the lights and now we're just talking purely about an inbound light coming from above us, and I want to look at what that looks like, what I can do is see how that diffuse lighting holds up now, right? Because now you can see that things that really don't get much specular bounce, right, still get some light when we have something coming from the top. And that's what we would expect, right? These are really brightly reflecting because they happen to point right there. And they get brighter as we get incident on them, right? Because that's that's the specular contribution coming in, right? And similarly, it's hard to kind of see them because it's hard because we don't have any that extend really that far downward. But as I get incident on these, right, they're dimmer there, they're going to be brighter here. But that's just, again, the diffuse helps keep surfaces from seeming like they're kind of doing mirror lighting, which is, not what most of our surfaces are going to be doing. So this is what we would expect here. And I think that makes all good sense. If we wanted to control the specular versus diffuse as almost like a slider, right? Then what we would need here is some information about the material, which at the moment we don't really have, right? We don't know anything about the material that we're sampling here. And that's something that we just haven't really addressed in Handmade Hero. We don't have any information about what materials we're sampling. We don't really know anything about them. We could have a non-per-pixel material, and we could have a non-per-pixel material specified fairly cheaply. That would just go into it would basically go into our pipeline where the color, where the color term goes in per vertex. That'd be a pretty cheap place to put it. If we wanted it per pixel, we're in a bit of a bind. The reason we can't get away with anything free there is because normally what you would do for most situations in 3D rendering is if you want to have stuff like material parameters per pixel, you can use stuff like the alpha channel of the texture, of a 4 wide texture. So you have RGB and then your like parameter for reflectance. We don't really have that luxury because we have sprites everywhere. So we use our alpha for saying how transparent is the pixel at this point. We still could do something there. We could split our pixel definition because it's arguable that we don't really need 256 levels of transparency transmitted in the textures. So we could say that our textures could have actual information in them about reflectance by saying that maybe we take the 8 bits and we split it into 4 bits and 4 bits. 16 bits of alpha, 16 levels of alpha, 16 levels of specularity. That's not a bad idea. I like that idea. We could totally do something like that. But at the moment, we're not really set up to do it anyway because we don't have an input for that. At some point, we could actually have a way to paint specular maps. You would import those into the games. So it's something to think about. But what I want to do is say, let's pretend that we can get something like that. And what we'll do now is just make it a constant. So right now what we'll do is we'll say like specularity or something, right? And this is just a random or spec mix, right? So a spec coefficient or something like that. And what we'll do is we'll say that there's a, well, I guess we'll call it spec mix, and we'll say, all right, let's say that surfaces are half and half. And then in that case, what we end up with is our spec coefficient is the spec mix, and the diffuse coefficient is going to be 1 minus the spec mix, right? And so in here, what we'd say is, well, this is going to be the diffuse amount, this is going to be the spec amount, and off we go. Oops. So you see how that goes there, right? And that's just saying, so now we can make our surface completely specular or completely non-specular based on an input value, and in the future, maybe we try and find a way to get that input value from someplace interesting so that it will vary, whereas right now it'll be constant everywhere. And so if we look, and by the way, I guess there's no reason for me not to be compiling in release mode so that our startup time is a little bit better there, right? I mean, we could just do that. There we go. And so if we take a look now at what's happening, so here we've got a 50-50 mix, which basically should just be what we had before, which is as we get sort of, things get brighter as we get sort of within them. What we can do is say, let's crank up the specular. So this is a perfectly specular one. So this should be back to just pure bouncy lighting, no diffuse. And let's just verify that that's what happens, right? So now I should see, like, everything should be angularly dependent, right? You can kind of see that now. This is perfectly angularly dependent now. And you can see it's getting brighter, these bounces, as I get close to incident, right? So that's what I would expect. Let's go pure diffuse. So now I should see no change from view angle. Viewing angle produces nothing. So now this should be just pure diffuse, no changes. And that seems to be right. And so then we can just pick, you know, what we're going to do. And, you know, I don't know what we want our surfaces to be specular-wise, but I'm just going to leave it at 0.5 as the mix for now, and we'll just call it a day. We'll revisit these when we want to actually do any kind of lighting effects, like surfaces that are supposed to be shiny or something like that. We aren't really set up to do specular very well because we aren't capturing enough information with our light probes, I don't think. Like, you know, we don't really have the notion that those light probes, the light probes don't store an actual image off in the direction, they just store a single color. And, you know, if we were going to be a little more hardcore on our lighting, we would store kind of more of an image. The problem is that just increases your per pixel cost, just goes up and up and up. And I don't know that we want to go into that territory. So if here we've got effectively our radiance sampling now working, we now pretty much have actual lighting working with our light probes for the most part, right? And so we should be able to do some stuff where we, like, I don't know, like actually put some fake lighting values in there, and then when we look at the scene, we should see something resembling some real lighting in there, right? And so if we look at what we're doing now, and we just change to that half and half, if we just said, all right, there's an upward lighting, we're going to make it just be straight up white light incoming. And we go ahead and look at what that looks like. We should just see a flat lit scene like this. But hey, it already looks a little bit interesting because there's at least some notion of directionality. So you can see that the light is kind of coming from the top down a little bit there, right? But we're not getting any bounce. It's not really very good, right? There's no real lighting happening here. And so what we want to do now is start moving towards the real lighting, and that's going to require the lighting transport. But first, let's stuff some lighting values in here that are based on location, so we can watch and see whether our light probes actually are being picked up correctly across sources. And more importantly, since I kind of think that they are because we did some testing with that, let's see if we can verify that our light probes themselves actually are what's what I'm looking for? That our light voxel is not producing artifacts. So when we stuff these light values in that change over the surface, over the voxel, that we don't see like weird bands or something in there that would indicate a bug or having thought through the problem incorrectly somewhere. So if I go into our place where we're stuffing our lighting voxels here, I need to do a couple things. First of all, we need to turn back on the repeated transmission of the lighting voxel, which is something that we had turned off for testing purposes. I believe it's off. And so if we want these things to move around, we're going to have to put that in there. So this only twice nonsense where we're sending this down, we need to get rid of that. Now, what I might do here is actually just if zero it out, right? Actually, I'm just going to nuke it for now. And so what we have here is every frame we will retransmit all of our lighting voxels so that they can be updated. And this is a sort of sore sticking point because we don't really know how much that's costing us in terms of frame rate, but it wasn't good when the voxel was big. The voxel's pretty small now, so maybe it's fine. But either or, you know, it is what it is, right? And so now let's try stuffing some real values down there that move according to some kind of a debug piece of information. All right, so the first thing I'm going to do here, not going to be very interesting. I'm going to do a light P, and this is just a light position value. And all I'm going to do is I'm going to take the distance from the light P based on the location of the location where the voxel is relative to everything else, right? And so what I need to know here, and you can kind of see when we do, where is that? Here we go. So when we do our in-lighting computation, we've got our render group here, and if you look at the render group itself, I believe inside that render group we've got the light bounds, and I think we also specify in the setup function, so in this last setup, that also tells us the voxel information. So if we look at render setup here, you can see that there's a voxel min corner and a voxel inf total dim. And those are pieces of information that we might want here to produce the information about how the voxel should be shaded. So if I want to figure out what's going on in here, we know that these values, like we want the we've got this light index voxel dim. We've got this inf total dim going on in here, which is being specified. You know, why did we have this? Well, I don't know. We won't bother talking about that. There's simplifications we should probably make here. But anyway, if we want to do our inf total dim, right, what we can do is we can take our voxel and we can do one of two things. I'm going to do it the way that makes the most sense based on sort of the way our voxel is set up and the way we're transmitting our values. But what we want to do is figure out for every point here, like where is this point in voxel space in theory, right? Like where should it be? And so if we think about where this point is, where its location is, right? So this is our voxel center P, right? We know that we've got essentially a X, Y, and Z value that is supposedly where this thing is, right? And those are just values that go from 0 to voxdim, so they don't represent world space. So the first thing we want to do is say, well, we can either map this out to world space, or we can map or we can map the light into voxel space. And I'm going to map the light into voxel space just because that maps a little bit better to what we're doing in the actual pixel shader. So what I would want to do here is say, well, the voxel center P is roughly something like this, right? It's halfway between the two grid locations. Presumably that's how we're sampling it. I have to think about whether that's actually true with the way that OpenGL is actually sampling it, but I think that is true because OpenGL I think uses textile centers for sampling, not textile corners. Even if you're sampling a voxel. So the voxel center should be there, and we need to change that to a UV coordinate. So then we've got like the Vox UVW, and that's going to be the Vox inv total dim, right? So that's the Vox inv Vox dim times that Vox center P, right? So that's a Hadamard kind of product there. We're multiplying each component, and we get back a UVW. So we need that value as well, and this is that inv Vox dim, right? And that's going to be 1.0 over Vox dim ad infinitum, because actually this voxel is the same in all directions. We don't know that that's going to be true forever, but for right now it is. So this is what our scaling factor would be, right? Our inv Vox dim is going to be that. We take the Hadamard product, that puts us into UVW space. And so then what we need to do is just say, well, where's the light? How far are we from the light source? So we have a light UVW, like where is the light in UVW space, right? And you know that's going to be something that would go up here. So we have to find the light in UVW space. We'll do that later. But for right now, what we need to do is say, well, what's the distance between these two things, right? So let's take the light distance. The light distance is going to be the length of the Vox UVW, the light UVW minus Vox UVW. That's the distance between the light source and our position, right? That's the light distance. That will be 0 if we're right on top of it. It will be the 1 plus 1 plus 1 square rooted. Square root of 3 if we're all the way on the corner, right? So that's the maximum distance that we could be away, I think, if the light's in one corner and we're in the other corner. So we want to make there be some kind of fall off here. So what I want to do is I want to say our light coefficient here is going to be getting less bright as it gets further away for no particular reason. I'm just saying we're going to do less bright as we get further away from whatever the light location is. And so I want to do 1 minus the light distance, but the light distance here, again, I want to do a clamp 0 to 1 on this because I want it to range cleanly between those. I want to do 1 minus whatever the distance away from the light source is, and maybe that's just fine, but then we may also want there to be some kind of a coefficient on this for the light radius. So like there's a light radius coefficient in here that we can play with. So that's like how, it's basically 1 over the light radius in UV space or something, right? And so this is what we would want to compute. We would end up with a lighting value here. And so what I want to do then is I want to make this value, which is the brightness, right? I want like light brightness or light base alpha, something like that. I want this value here to basically be computed now so that we can make the intensity of the light be what we start with. And that way, when we put a light in here, it will be based on this actual distance from the light source, if that makes sense, right? Now, there's other things we're going to want to do here. So we're going to want more information. So I'm going to make a light direction as well. And that's going to be this value. And I'm going to normalize or 0 that probably in here. And again, this routine is going to get really slow. So we're going to end up with some issues here. But, that's just something we're going to have to deal with because this is only for debugging anyway. So anyway, as we do this sort of normal to the light source there, we're going to end up with some more information. I'm going to call this light disk to be clear. So as we compute these values here, now we've got more information about the light source. And what I want to do is pack that into this light base A, right? So all I want to do there is say, well, it's already clamped from 1 to 0. So really all we're talking about here is taking that light coefficient value, which is basically the intensity of the light source. I want to multiply it by 255, which is the maximum value it could be. Then I want to convert that to U32, and then I want to shift it up into the alpha channel, right? And that's all I'm doing. So that's how I'm going to create my light base A. Unfortunately, in order to do that, I need a light UVW here, which is the location of the light source relative to the voxel. For now, let's just call that 0. So it's always going to be the corner of the voxel. Actually, you know what? I take that back. Let's make it the center of the voxel for now, right? So your distance from the center of the voxel is what's going to determine your lighting, and we'll start with that, right? Light RC is, I don't know, 0.5 as well. All right. All right, so we're going to have to make those values be real things, but now basically what we want to do is see if we can get this stuff working. Now, this looks super crappy, so obviously I screwed something up. Not sure what yet, but we'll find out in a second. Looking at the Vox UVW there, that seems like... So one thing that's true that this light C may be, yeah. I mean, I feel like maybe we may want this to be higher than that. And the fall off is probably not gradual enough. The interesting thing about the light C is this is the maximum intensity light. So we really don't want this light to be maximum intensity, is the other problem. If the max light intensity is 10, and we want this light's intensity to be something else, we want that to be kind of reflected, pun intended, in here. So we want a light intensity value that's probably not the full intensity, so we probably want like max light intensity to something like, you know, this is only a tenth of the maximum lighting intensity or something is all I'm thinking, right? So let's see if that produces anything a little bit more interesting there, but probably not yet. So we've got some weird bugs here. It looks like we're stuffing really bright values in here always, which is a little weird. So let's try and figure out what I screwed up there. We've got the Vox Center P here. We're taking the Handmade product to figure out where the voxel is in UVW space. We take a difference between that and the center of the voxel, basically. We look at how long it is to get there, and we normalize that afterwards, but we don't actually use this. We look at the light coefficient by saying, well, all right, the fall off should be however far away we are from the light. As that increases, we should end up getting something where at 0 we have a full bright, and as we get up to like whatever light RC is implying we are, this should probably, you know, maybe we need to make the fall off be faster. I don't know. I'm just wondering why we don't see any fall off, but maybe that's because I was being too generous with it. I'm not sure, but we'll see. There we go. All right, so I just had the fall off too far, right? So here's what our lighting would look like as we go. And you can see the voxel itself represented there, right? And since our voxel is not stable right now, it moves with the actual character quite a bit. But you can see, so the character hops up and down. That's because of our Z range. That's something we want to fix anyway, so I'm not worried about that hopping at all, because that's a separate thing. And you can see the hard edges of the voxel right now because we have interpolation turned off. So as we sort of look at that lighting, it actually looks like what we want, which is just a purely distance-based light. It's what we expect to see, so that looks nice. But we don't want those hard edges. Let's go ahead and turn on the interpolation on the voxel just to see and make sure that that looks okay. Because now that we've seen the actual like voxel size, we don't really need to see it anymore. I mean, maybe we want to turn that on occasionally just to, you know, debug something. But at the moment, I think we certainly don't need that. So if we do a search, for nearest we should see that's in here. Here's our voxels. There's the nearest sampling. So if I tell it, no, I would like you to do linear, please. Now when we run, we should see something that hopefully approximates decent lighting. And you know, it's not perfect. I do see kind of at the edges, I do see a little bit of sort of banding. I'm not sure what I think of that exactly. Just looking at kind of like these parts, maybe there's a little kind of voxely banding, like do you see that? Kind of right there. So I don't know if we're gonna have to work on that a little bit. You know, maybe we will, maybe we won't. Because you can see now, you kind of see that stair-step pattern there. And I'll be honest, I don't really know exactly where that's coming from, though. I'm not sure, yeah, exactly where that's coming from. So it's hard for me to say whether that's something that gets fixed with lighting sampling or whether that's an inherent limitation of the way we're doing the light voxelization, right? But you can definitely see some objectionableness to the way that that's being sampled. And that's, I think, just kind of a property, unfortunately, of the trilinear interpolation on the voxel, I'm assuming, but I guess I don't really know, right? So if we were to make this fall off be, you know, what I really want to do is make it locked to the player. So let's finish what I was going to do, which is to actually map a real light location in there, so that we can talk about the location of the viewer and like have a debug light kind of a thing. So when we come through here, if we mapped the location of the light source in here, what we want to do is say if there was a light P, so let's say the light P value was something that we're going to pass in. What I want to do is have a way of computing the light UVW value, which I believe all we would need to do there is if we take the render group and say, or it's just called group. Just called group. If we were to look at what we used for the lighting setup there, what I should be able to do is just take that pair of parameters that we're using inside to map and say, well, we know that the voxel min corner is what we need to subtract away from a position to base it around the voxel. And then we know that the inv total dim is what we use to map something into the scale of the voxel. That should produce a UVW value for where the light source is in voxel space. Assuming that we had one, right? Which at the moment, unfortunately, we don't. So we do need some way of getting that, which we'll take a look at in a second. But oops. Forgot to change that to a comma. So now, as long as we have a way of passing in a debug light, which we'll do in a second here, we should be able to now actually make this based off of the player's position. And what you can see right now is it's just based off of 0, 0, 0 in world space, which doesn't really give us anything we didn't get before. But you can really see, you see those kind of objectionable, like, blending? It just doesn't look very good, right? You get that kind of, that rippling there, right? And I don't love that. Like, so I don't know what we're going to have to do about that, but that seems bad, right? So we'll see. Anyway, so moving on. if I want to go ahead and have this be locked to the player, which I kind of do so we can sort of see how that sampling works, what I want to do is have some way of sending down where the player actually is. And in the world group, in the world mode, we do know where the player is, right? Because what we're doing when we actually do stuff like tracking the movement for the entities, where is that code? It's right here. So when we do this, you can see we know like what the camera entity is. And so in here where we say world debug light P, like we know where the debug light is supposed to be. It's right there, right? So all we really need to do is when we do the end lighting computation, what we could do is say, well, you know, the test lighting debug light equals, you know, this other debug light that we've got here. And so inside the lighting stuff, we can just for free have this idea that there's a debug light kind of smutzing around on us here. Like that. And then we should be good to go. Because we already tracked a debug light position for, you know, for fun and profit before. And so what we can do is have another one here. So the lighting system itself now has its own debug light that you can stuff with whatever value you want. And when we turn on this debug mode here, that's what we should get, right? So now as the player moves around, right, the light should move with them. And you can see that sort of, you know, that radius around them occurring, right? And so I guess the thing, yeah, like I was sort of saying before, the thing that I don't care for here is I just don't like what's happening with, I think this light sampling just isn't good enough. Because I don't like the way we're getting those hardline artifacts where the lighting sort of falls to zero. And that you know, what that kind of means to me as well is it's like, it also means that that artifact is sort of present everywhere, right? Like, you know, you're getting that pretty much wherever you go. So anywhere in the world where you actually see lighting happening at all, you're going to be having this artifact. It's just a lot harder to perceive when the values are close together. But as the values get a little further apart, you get that stiff banding, right? Now, maybe the argument is, well, you should never really have values that far apart because the lighting is supposed to be fairly continuous. But I don't know that that's a very good reason to have it look the way that it does. I think we want to be able to have it sample the lighting well in any case, right? And so I think I at least want to try to get that a little better. And what I would assume is that, like, you know, the reason we tried this was because it's a lot simpler to blend the light probes this way. But there were, like, you know, there are other ways that we could have done the light probes, right? And it's a lot simpler to blend the probes this way than it is to blend them the other way. So, you know, rather than using a voxel lookup into a light probe array and then blending the light probes sort of that way, which was much harder. In this particular case, what we decided to do was just use the voxel, use a 3D texture to sort of look up the lighting. But unfortunately, you know, it looks pretty bad there. Now, I guess the other thing I don't really know is that an artifact too of kind of maybe more how we chose to sample this? You know, like for example, suppose you wanted a less hard fall off curve. You know what I'm saying to you? So, you know, if we take a look at that, how do we get this thing? There's this good site, Desmos, we were using. Here we go. So if we wanted to look at like what we're getting for fall off there, right? We're getting like within one radius, we're getting like an x squared plus y squared fall off. I don't know if this thing can do that. But, well, it doesn't really matter that much, I guess. The point is, like, let's suppose we just looked at the fall off along a diagonal, and so we said it was basically the square root of x squared plus x squared, right? And really, you know, what we want to do is look at it like this, but this would be a 3D, and I don't know that this thing can do that. So I'm just going to go ahead and assume that, you know, we just do x squared plus x squared, right? So the square root of x squared plus x squared, that's going to be the fall-off equation for our particular light, which, right, it was 1 minus. And so we had some coefficient in here which we can use to sort of change the angle of this, right? Like if it was that, it would take longer. If it was that, then it's steeper. But basically it's linear, right? And so what we could do if we wanted to is, if we want to smooth this out, we can look at this function. And God, this interface sucks now. Was it always this bad? I just want to put this whole thing into the square root. So we can see that would be a steeper fall off. All I was trying to do is illustrate the difference between these two things. And this would be a smoother fall off, right? So I don't know, like we could say, well, how bad is it if we assume that the lighting isn't as harsh? You know, it doesn't fall off as harshly. So with this clamp 0 to 1, maybe what I do is say, well, okay, like, yeah, we've got light C times equals whatever the light intensity actually is. But before we do that, we want to smooth the fall off curve. So we just say, like, well, you know, square that, right? And so if we square that term, we just get, you know, in theory, a smoother fall off curve. And how bad is that, right? And the answer is, you know, it's true. It's not as bad, right? But it's still pretty bad, I would say, you know? And it, you know, we can sit there ad infinitum making this less and less harsh, I think. But I don't think we're ever really going to get away from that artifact, right? So here's, in fact, that one really looks worse, honestly, right? Because, of course, it's weaker, right? So I think we've learned what we want to learn from this. We can also try a harsher fall off, but I'm assuming that's going to be bad as well. Wait. Oh, you know what? We don't call it square. We call it square root in this program, right? I'm assuming harsher fall off will be just as bad as the really unharsh fall off, right? Did that not work? Syntax error. Yes, I agree. There we go. So I think, yeah, I think we want to do some more thinking about this, right? Yeah, you can see, like, look at how much blockiness you get at the edges of that one, right? And we can take the light intensity down to see what it would look like more reasonably, because, like, that light intensity is too high right now. But it's still, you know, you're going to get that really hard fall off there, and it happens pretty much in either case, right? So I think there's no way around it. I think we're going to have to do something better, right? I think this is just not good enough. And that's kind of unfortunate, to say the least. But I think that's basically where we're at. So, yeah. So how much time we got here? We've got about 15 minutes left. I guess what I would want to try, and we're going to have to think about this a bit. So the next thing that maybe makes sense to try is to say, what if we actually just compute like lighting distances? So we actually think about, for the voxel UVW, we say, where are these lighting probes? Where are the centers of these probes? And let's like actually try to shoot light towards them so that we blend radially instead of trilinearly, right? Like, that's my first thought. My second thought is, well, you know, since this stuff is being sampled as like more of a well, you know, is what I'm saying actually true? So the thing that I'm thinking about in my head is just like, well, you know, we've got light sources, and those light sources are not have, there's no direct illumination pass in Handmade Hero, right? So we only have the indirect illumination, and that was really all we were planning on really doing. So we're not doing like shadow maps or anything like that and projecting lights as specific lights. We just have like a lighting sort of convection phase, and that's it. And so, you know, I mean, one thing that I guess you could say is the situation specifically that we're talking about here, where you get like fall off of the light, you know, based on the distance from the light source, is not really ever going to happen. So I guess it's possible. I mean, it's I don't know for sure, but I guess it's possible that you would never really have something like this happen anyway. So maybe it's the wrong thing to say, let's get rid of it altogether at, you know, right away, because, you know, I don't know, maybe we don't actually need to get rid of it. Maybe it's fine. And maybe if you're talking about lighting that is always got, you know, sort of the first pass with the probe distribution already having smooth the light out around so that, you know, things are generally lit, things next to each other are pretty similarly lit, you know, maybe you just don't ever have that particular problem. And I don't know, right? So it's really hard for me to guess. It's pretty difficult for me to make a specific guess about that. So it's hard to say. You know, on the one hand, I'm like, should I just go in then? Should I, you know, should we go forward with this light sampling and then, you know, do it after the fact? I don't know. Maybe we should, because maybe it's putting the cart before the horse to try to improve the light sampling. And maybe we should see. So let's do one more thing before we end for the day. We've got the light normal here. Let's use the light normal to decide who we stuff, right? So we have our, you know, up, down, north, south, east, west, just to put some different lighting directions in there and mix it up a little bit. And so what I'd like to do here is say, all right, let's take a look at which one of these components is maximal. Or maybe we'll just say, we'll use the light and itself to determine who gets what light where, right? And so we'll say, okay, there's going to be a light stuff value here. I might go ahead and make a little utility function for this. Well, you know, we could use an RGBA pack 4x8 here. I guess it's a BGR pack technically. So I could use this. So we basically we call this on each one. So instead of doing it this way, we would do this. And then what we would do is all we would do is have actual light values here. So we'd pass in a V4, right? And the V4 would have the alpha or the intensity for each channel. So this is the west intensity or the west alpha, I guess you would say. And then the light color, right? So this would just be, you know, that for now, but we could obviously change the light color if we wanted to. So we'll do something like this, I think. And then we just need to actually compute those alpha values, and we'll compute them based on the lighting direction there, right? So here we have south, north, down, and up. And then all we need to do is actually produce those light values ourselves and you know, get them in there. So we don't need this anymore. We'll let the pack work generically. So looking at what we've got here, we can see we've got a light. This is the direction to the light from the place in the voxel, which is what we want to use for packing. So what we want here is to produce values for each of these. And this is how much of the light is coming in from that direction, right? And so what we'd like to do is we'd like to basically, you know, maybe use the dot product here to say, like, how close are we to that? This is not exactly right because we're trying to conserve the amount of light. So we want all of this to sum to 1 in a sense. And so, you know, it's something that we want to kind of do a 1 norm on probably after the fact to make sure that we don't add light to the system. So it's more, we got to be a little bit flexible here. So we'll try to figure that out in a second. But anyway, so if we take these values here and first compute them as clamp 0 to 1, you know, light n. And we don't actually have to do, because we know that these are all cardinal directions, what we can do is just take the dot product manually. We know that the westward facing one is going to be whatever the x parameter is negated because you're multiplying it by -1, right? Same thing here. This is just, you know, each one of these, we can just pre-evaluate the dot product, right? So we know each of these is going to be the normalized light value, basically like with these pre-dot products computed. And then what we need to do is say, well, that's how much is contributed to each one, but this is not going to sum to 1, right? And so what we then need to do is make sure we don't distribute too much light into the system. So at that point, we would just sum them all. And then we just need to do the inverse of that, right, to like fill it in. So we would need to say west A, you know, divide equals total A. Right, each of these, east, south, north, down, up. And then we know that we're not like making too much light because we 1 normalized it, right? And I'm not going to guard for 0 there, although I probably should. I guess I should because this can technically be 0. So maybe I'll do this. Right, and then this is just a multiply. And that's just if you happen to be standing like right on the light source, you don't know which direction it's coming from, right? Well, and actually, so that's a safe ratio 1, technically, right? Because if you're standing right on the light source, you should get it equally from all directions, not get it at all. So I think that's actually, it should be that. Okay. Wow, that went poorly. So what did I script there? Anyone know? We're computing the light normal. We assign it to each of those safe ratio 1. We multiply by the inverse to 1 normalize. We then do a BGR pack. That looks good, doesn't it? Is this just busted? I wonder if my pack is broken. Yeah, it is, apparently. All right, so my BGRA pack 4x8, is there something weird? Oh, yeah. Gets me every time. So these are 255s. So this is actually this. Here we go. There we go. All right, so taking away the Fulbright up A nonsense there. The other thing we need here is this is not respecting, this inf total A is a little bit wrong because we have a light intensity value, so we want it to sum to the total light intensity, right? Or rather the total light C, contribution level, right, I should say. So what we want to do is say this is the total light contribution. We're going to spread it out this way. So we want to say don't normalize to 1, normalize to whatever the total amount of incoming light should have been at that point. And we'll do it like that, right? And that's just the radial fall off curve, right? So here is our, directional version of this. So now we actually have the light coming from different directions. And you can see that it actually is as well, because if you look at what happens, say, on the wall here, right, you can see that you get like curvature coming in. So the surfaces themselves are not uniformly lit. It depends on what direction you're facing, right? So that does seem to be working, and we see exactly what we would expect to see there, like darkening in that corner, right? Because again, it can't, when it's pointing in the different directions there, it's gonna fade out that earlier, right? So we do see that. I think that's what that should look like. It just looks fairly right to me. So that all seems pretty good. Let's take a look at what happens when we just go into something that's a little bit more vertically stacked. So here you can kind of see, and I don't know if those normals are correct or not on the sprites. In fact, I kind of wish we'd turn those off, because I should probably go verify that the normals are correct is what I should do as sort of a separate issue. But it's hard to really gauge whether that's working properly. But it sure seems like it is. And the only thing that I think isn't quite working properly is I don't think these I don't think the sprites themselves have their normal set the way that they should be. So I do think we want to take a look at that. And if I remember correctly, there's some kind of nonsense happening there with normals that I don't really remember what it is, but like if you go look at the entity output stuff, I feel like there's some nonsense going on in here. So if we look at the way that we're spamming these values down, there's a cover n value here, and like looking at this, it's kind of nonsense, right? I'm not sure exactly what we want that value to be, but it's probably not that, right? We'd have to think about it, but it's probably something more like this. You know what I'm saying, too? So we'll have to think about that and whether or not that normal's coming through correctly. And we probably want that normal to vary as well. So we probably want that normal to actually be like something that changes over the surface of the sprite as well. So let me just take a quick look though. And you know, for ground cover, it almost seems like it wants to be lit more with the actual ground that it's on. So I wonder too if maybe that's not the right thing for cover sprites. Cover only. Actual upright sprites that are, you know, not just ground cover, maybe don't want that. Because then you would get the lighting that you get for the ground, which seems like what you want, so that the ground cover appears to be lit the same way that the surface underneath it is, right? And then you should see them getting sort of more uniformly lit, right? And maybe that's what we want. I don't really know. Kind of hard to say. I also do wonder what happens with like a sprite like that. Looks like that gets lit pretty correctly there. But as we get behind that guy, they should be darker. Yeah, which is exactly what we want. So yeah, I mean, it looks like our lighting sampling is working pretty good. I just don't love those edge artifacts. Let's go ahead and go to the Q&A. You know, we're not horrible. I could see shipping this because, you know, people have shipped a lot worse. But I do think spending a little bit of time, maybe not now, maybe we should just leave it this way and go do our light transport and then come back to it. But I do think there's better things we could be doing there, and so I don't know, right? But yeah, so I think we'll I think my gut inclination, if I had to say, is I think what we should do is, this is good enough for now. We should ping pong over to the light transport, get the light transport working, ping pong back to the sampling, and then improve the sampling based on what we see as a result of the light transport stuff, right? I think that might be more what we want to do. So, do we have any questions? We don't have any questions, apparently. Could you give a sort of brief high-level explanation of how the lighting works? Or two people asked questions on that. Could you draw a quick diagram giving an overview of the stages in lighting position? Sure. We don't really have any questions, so that seems pretty easy. Let me field these in opposite order though, because somebody took my name. Also asked, are the cube artifacts a result of the view vector reflection instead of the light vector reflections? So it is worth noting that we don't really know what those artifacts are exactly. I think they're just would happen anytime you're doing that trilinear though. But let's double check, right? So if we do compile z-bias program in here and we look at how the lighting is working, right? What we could do is say, well, you know what? Just get rid of the specular. So that way, all we're doing is pure diffuse. So, you know, goodbye specular. It's gone. And now, like, what does our light sample look like when it's only sampling diffuse lighting, right? So if we're only sampling diffuse lighting, this is what we get. And to me, that looks the same, right? So I don't see any... The artifacts look like they look. To me, right? They look like they looked before. So I'm assuming that our specular reflection equation doesn't really have anything to do with the artifacts. It's just the trilinear interpolation in the voxel that sucks, right? And I can understand why that would be, because what effectively is happening is we don't blend the light probes and then take some aggregate light and sample the aggregate lighting. What we do is we blend directly what we think the incoming light from that direction is on the voxel. So at the place where it goes from something to 0, there's just a hard trilinear edge there, right? So it's not going to give you radial fall off like you would expect for the diffuse lighting. And the only way I think to really get that radial fall off is to be using the distance to the voxel as part of it, right? Now, maybe the answer is we should be doing that so that it's a radial fall off, but in order to do the radial fall off, you can't use the trilinear anymore, right? I mean, another answer is, like, and another question, the first thing that came to mind was sort of like, what if we just sampled the light from all of these cube maps based on normal? I don't know. So I really don't know. But let me go draw the diagram anyway, because that was the question that was asked. So the lighting stages are pretty straightforward, actually. There's not that much stuff to it. It's just that because there's like the need to persist over frames and you know, optimization concerns and all this, it gets overcomplicated, which is why lighting always is bad. I mean, lighting should take like 5 seconds to implement. It's just a ray tracer, right? And then the lighting's perfect. The problem is that's way too slow, right? And so everything is about all these like hacky approximations that we're doing to try and not have to do that, right? So anyway, the stages are pretty basic. So basically, this is at startup, and this is at runtime. So during startup, the first thing we need to do is light probe distribution. And what that effectively does is it says, well, you know, we generated some stuff, like, I don't know, here's a room, and there's a doorway, and then there's another room over here or something, right? And so whatever the heck we generated, we need to distribute light probes. So we put them in the environment wherever we think we might want them, right? And it's just a hacky, random thing. We can spew them out wherever we want. It doesn't really matter. So we have light probe distribution, and that distributes light probes through the system, right? those light probes are actual entities, so they go into the entity system. And the reason for that is because we're just using the fact that we have a nice, robust entity system with caching and all kinds of stuff that allows us to have like billions of entities if we want to. So it's nice and free to just throw the light probes in there, and in they go, right? Then at runtime, what we have is a thing that's basically like a light table. So light probe table of a certain fixed size, right? And so this is like n long, whereas this is like arbitrary, right? So the number of light probes, the number of probes is like, you know, basically infinite. It doesn't, like, within machine storage, we don't care how many light probes the world generator generated. It doesn't matter. At actual runtime, some number of these light probes, right? We have a light probe table. So step 2 in the process, and the first step that happens at runtime, because this one happened when we created the world, is like probe index assignment, right? Can somebody please tell me if Milton's been fixed, by the way? It's so bad to draw on now. It like totally broke. And I don't know why it broke, because it was good before. I'm not sure why they broke it. But somebody broke it, and I'm not sure what the deal is with that. Anyway, so probe index assignment just basically says, look, some subset of the million probes or whatever that we put in the world, some subset are actually useful right now. And what we're doing is, as we move around the world, we're sort of taking some subset. So maybe we say, like, you know, these probes right here, we don't need anymore, right? So this is like, you know, removal. And then some new probes came in, so then there's like insertion. And we like use those spots that we pulled stuff out of, and we stick new light probes in there. So we have a light probe table that is basically just a way of maintaining a small number of light probes that will actually go into the lighting system, and that can be indexed by the hardware as necessary, right? And what we're doing with this is we're storing the light so we can have what's called hysteresis. I'm not even going to try to draw that with the new Milton. How do you spell that? Hysteresis. There we go. So we're trying to get some hysteresis in there, which is basically to say that, look, our lighting is going to be very noisy. We know it's going to be noisy because we can't afford to really do light computation. We are not on like an RTX 2080 or something here. And even if we were, most people who do that still use hysteresis. So we kind of need to smooth these values over time. So what we're going to do is we're going to take this grid, this array of light probe table, and we're keeping it. So this is like persistent frame to frame, right? So we want this to persist frame to frame, and so what we do is, you'll see that when we get up here, we're keeping this so it has a value from the previous frame, and that's what the lighting was at each probe on last frame, right? So then what we do is we say, well, okay, we assign probe indices, so people who need indexes get them, people who are old and have fallen out of the view, frustum or whatever, get their indices removed. Then we do step 3, right? Which is like light injection. And all this is if we have actual light sources, those get, you know, rendered directly in. So we need, and we haven't done this yet for the new system. We did it for the old system, haven't done it for the new system. So actual light sources get specified by entity output, right? So somewhere we're going to have to, like, you know, we've got the thing that can say push light. That push light records the fact that someone's actually emitting light in an area, not just bouncing it around, right? we don't do this yet. So we were doing it with the old system, and the new system we haven't done it yet. And we'll get to that at some point once everything else is working with debug lights and so on. Okay, then step 4 is, light transmission. And so what happens here is we say, all right, let's take all the light probes that are actually in the view. So we've got, some light probes here. Let's just see, cast rays out from these light probes and see what they hit. Sum those values up to produce what's basically like a, new light probe set, right? And then we smooth it, right? So here we say, smoothing. This is the word I can't spell, hysteresis, right? So what we do is we take the new light that we have and we multiply that, right, times some small coefficient like 0.05 or something, right? And we add it to almost entirely the old one. So this is the old one that we had way back here, right? And what that does is that allows us to average over, 100 frames or something. Let's say we made it like 60 frames, but it's any number we choose. So 1 second worth of gameplay. And basically what we're doing there is we're trading off responsiveness. So lights will lag in their effect on the world by about half a second on average, because it will take a full second to respond completely to the light. So the time the user actually sees like a prominent effect from the light would be like half a second or something in. So you're trading that for noise. Because if we just drew the light directly, whatever we calculate on that frame, it would be very flickery. Because we're not casting enough rays to actually capture the complete lighting environment. So what we do is we take the average over several frames so that we actually have way more light rays that we're actually using on any given frame, because we're using the ones from last frame, and the frame before that, 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 right? And that's the entire light pipeline, really. After this all happens, we do have the part that happens on the GPU, right? And what we're doing there is the part you just saw. We have some voxels. Oops. And what we're imagining, and don't do yet, is right here, there is a voxelization step of the light probes. And the reason that we don't really know exactly what this looks like is because right now we're not sure if it's the right way to sample. This is why I was saying, well, I'm not sure if this looks good enough, right? But what we would say is, well, we have this array of light probes. We will voxelize the light probes. We will send the voxels down to the GPU, and then the pixel shader, right, will sample them, right? So we sample the voxels, and it's up to us how we choose to encode them. Right now, what we tried doing is 6 times the voxels, where we put each direction of each probe into a separate voxel. So we basically would say, like, okay, we voxelize the directions of lighting in the probe into 1 voxel per direction. So we actually have 6 voxels. We trilinearly sample each voxel to get the average incoming light from that direction, right? And that's what we use. So Caldevu says, responding to why there's not 2 cosine terms, 2 things. The BRDF is defined to be the derivative of the outgoing radiance with respect to the irradiance, so whatever extra terms you think you need are already folded into the BRDF. Okay, so basically, if we were to use an actual lighting BRDF, it's already got that accounted, so that's fine, and that makes sense. Also, remember that the next bounce of light will have another cosine, so the other cosine is accounted for. Does that clear it up, or am I misunderstanding? So it doesn't clear it up for the I, because the I doesn't have that cosine term in there. So I guess I'm not sure about that last part. But yeah, if the BRDF already has whatever random transmission is going to happen baked in, then sure, that's fine. But we're not actually doing that here, so I'm not sure whether that counts for when you're not using a BRDF, right? But hard to say. And 0LPBM says regarding Milton, aren't using an unofficial version that has the grid tool patched in? If so, maybe switch back to the official version. Yes, I am using the unofficial version, but according to the person who made this unofficial version, the official version also has it. The reason we didn't have it before was because I was using an old official version. So apparently what happened is somewhere along the line between the old version we were using and the newest official version, they broke it. Supposedly. So I was hoping someone would fix the official version to not be broken anymore, and then we could have the grid tool and reasonable sampling. If not, I can try to roll back to whenever the Milton is that doesn't have this problem. All right, looks like we're all done. Let me go ahead and wrap it up. Okay. Thank you, Ed, for joining me for this episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the series at home, you can always pre-order the game at handmadehero.org, and it comes with a source code, so if you'd like to play around with it, you can do your own experimentation at home. Also, now might be a good time to do said playing around because you have all day today, and possibly quite some time if I choose to work on the light distribution function stuff tomorrow, to figure out what might be some better ways of doing light probe sampling that don't have the artifacts that we were seeing with our trilinear filtering there. That would be a fun thing to play around with. It's a very well-constrained problem. You can think about it. You can play around with how we're doing it in Handmade Hero and see if you can find a better way to do it. There's also lots of research in this topic. You can go look up papers on light probes and how they work and how people use them. And so maybe get some ideas of how to implement something closer to a full-fledged thing. I don't know. But point being, there's a lot of work you could do there, so it might be a good time to play around with that if you're looking for something to do for practice. That's about it for today. I'll be back here tomorrow, same time, same place, for some more work on the lighting. It's looking like we're getting there. I like where we're going with it, but you know, there's still a lot of work left to do. So we're going to be doing that work until we get it just right. That's it for today. Hope to see you back here tomorrow. Till then, have fun programming, everyone, and I will see you on the internet. Take it easy, everybody.